Okay, so welcome everybody to today's Colkin seminar. Our speaker is Antonio Jiménez-Pastor, and he'll talk about approximate constraint lumping for dynamical systems. Please.
Thank you very much, and thank you for the organizers to invite me to give this talk. I'm going to present here an extension of constraint lumping that is approximate, as the title suggests. And this is a joint work that we've been developing with Alexander Leguizamon Roballo, Mirko Tribastone, Max Tchaikovsky, and Andrea Vanding. So let's jump in. The talk will go more or less as follows. First, I will remember what lumping is and how these model reduction techniques work in a mathematical sense. Then I'm going to present this numerical or algorithm that is an extension of the current existing algorithm CLU that precisely attach this problem of constraint lumping in an exact framework. And then I'm going to explain first why we want to have this numerical glue, what advantages we have, and all the details necessary to adapt the algorithm to this numerical version. And then I'm going to show you some experimental results that we have applied into some this new technique into some models coming from biology. And we will want to show that even we have this numerical approximation of a lumping, then we won't incur into big simulation errors at the end of the day. So let's start with the first point, which is what is model reduction, or what is lumping in this case. So let's start defining what is the setup of the whole problem. We are going to consider this first type order differential systems, where we have a function f that maps n variables to n values. And basically we have this first order differential system where the derivative of the variables is just the evaluation of this function at that point. One could see this as an autonomous system, but you can also have time-dependent functions here, just adding a new variable and adding the corresponding equation. And the whole goal of this model reduction technique is more on lines like we have n variables. This is the dimension of our system, and we would like to reduce the dimension of the system somehow, usually in applications when people from biology or engineer, they build this type of dynamical systems. They build something that requires a lot of information, and at the end of the day, they are interested in the values of some variables here and there. And the question is, can we reduce the system in order to do the simulation faster because we require fewer variables? So that's more or less the setup for model reduction. And the actual technique that we are going to study here is lumping. So what is a lumping? In this case, we have the system x prime equals f of x, and we say that a matrix L that goes from m variables to m values is a lumping if the new variables that are defined after applying L to x, so essentially these new macro variables are just linear combination of the original variables. They are function on the x's, so you can compute their derivative, and these derivatives are function on x. Perfect. But we say that L generates is a lumping if these derivatives of the y's only depends on the y. So you can rewrite this right-hand side that you get after computing this derivative here, and then you get just a function in y. As an example, let's consider this dynamical system of three variables. X1 prime equals to this polynomial in x2 and x3, x2 prime is this polynomial, and so on. And then we can check that this matrix L is a lumping. If we analyze this matrix, the first row tells us that the x1 variable remains by itself, and then the x2 and x3 variables are combined by x2 plus 2x3, and then we get here, like we show, the new macro variables y are just x1 and x2 plus 2x3. And then if we just compute here, y1 prime is just x1 prime, we go to the system, we plug this in, and we realize this is just the square of y2. So yeah, good. A function that only depends on the y's. Then we go to y2 prime. And then we compute the derivative of this sum. Since everything is linear, is nice, is a derivative, everything moves nicely. And we use the equations of the system in order to get the final expression. And in this case, it turns out that this derivative is just minus 2y2. So we managed to express everything in terms of y1, y2. So this is a lumping. So then the question that comes is, okay, lumping allows you to basically reduce the system from the original variables x's to the y's. So how can we compute a lumping? Or let's start with a simpler question. How can we check if something is a lumping? So thinking about what being a lumping means, we can look to it from a functional perspective. And in this case, by the definition, L is a lumping if there is a G such that we have all that line. So let's analyze it bit by bit. The definition of lumping tells us that the derivative of y's is just a function of the y's, g of y. And since y is already L of x, then we have that this is precisely this composition of functions. So you compose the g and the linear map induced by L, and then you apply it to x. And then if we go to the other direction, right, since we can apply just the nice formulas for the derivative, since y is L of x, then you have that y prime is L of x prime, and then this induce this composition L composed with f. So if we just draw a diagram that we all love to see, essentially we have by the problem the f function, and the L is kind of the matrix we want to check if it's a lumping, and L is a lumping if and only if there exists such a G that makes this diagram commute.
Can I ask just a quick question?
Yes, sure.
So there is no requirement. So in general, in this model reduction, there is no requirement that you're able to recover the f from the G in any way.
No, usually no. There is no necessity to recover, because usually what will happen is you are focused on some parts of the model that you want to compute with. So then once you have that part of the information, you are not required to recover the whole f, and that's precisely one of the key points of this lumping technique, right?
Okay. Okay, thanks.
Okay. So, okay, this is more or less the functional perspective on a lumping. Now let's go more algebraic. And it was proven a long time ago that having a lumping is related to the Jacobian matrix of is related to a property of the Jacobian matrix of the function that defines the system. So, long story short, if you have L that is a matrix, and you have the Jacobian of your function f, which is just the matrix which each row is just the gradient of the components of f in each of the variables, then L is a lumping if there is a matrix A of x depending on x, such that for all points in the space this kind of rule holds. So essentially you multiply the Jacobian by the left by L, and this has to be equal to the A that has to exist, which will be related to the G in the function before, times the L. Or equivalently, you can see that the rows that are generated by L times the Jacobian can be generated by the rows of L. This is another way of reading this formula over here. And afterwards, this criteria was used by Ovchinnikov and company to develop an actual and effective algorithm to compute lumpings, or at least to check if something is a lumping, because in the case that you have a polynomial f, then the Jacobian is also a polynomial. So you can split it, the Jacobian matrix, into a sum of constant matrices and monomials that just appear in your Jacobian. And then the criteria tells you that L is a lumping if and only if there are constant matrices now, A of t, such that for all the monomials, this type of commutation holds, right? So again, the rows that appears in L times J of t can be generated as a linear combination of rows of L. And yeah, so this is more or less the way of checking that a matrix is a lumping. And the talk is about constraint lumping. So far I'm talking about lumping, and as somehow I was mentioning before, modelers or people that use these techniques usually focus on one part of the model. So usually you don't need to compute a general lumping. In fact, computing a general lumping that kind of define what a minimal lumping is, or computing different chains of lumpings here and there, is not trivial, and it has been studied by Dimitraki and Pogurin. This year they have a nice publication studying this general lumping without an observable, but in this work we work with constraint lumping, where the user essentially give us some quantity that they want to observe, and this is this observable X that will be a linear combination of the original variables. So for example, you can say that I want to observe X1, then this is my observable, and the corresponding matrix will multiply the variables to get this X1 variable. And then I will okay, so once we have fixed the observables, a lumping is set to be constrained by this observable if I can recover this part of information. So these observables are the key thing that I will recover from the system, or those observables are the things I'm interested in. So that's the only thing I need to represent with my system. And that, algebraically speaking, is just that if L is a lumping constraint by the observables, if there is a combination of the new variables, the y's, such that my observables can be obtained from the y's. Or if we expand all these expressions, it's equivalent that M, the matrix that defines my observables times X, is equal to A times L times X. Good. Yes, so essentially, as I was saying, this tells you if you have a lumping constrained by some observables, you can recover these observables. So you can recover this part of information. And it was explained in the paper by Ovshinnikov and people and more and collaborators. Then you can develop an algorithm that computes efficiently the minimal lumping constrained by an observable set. And in fact, the idea behind this algorithm is simple enough that if you say, okay, I want to observe something, I will just keep applying these matrices that I need to be invariant under until I reach a fixed subspace that I don't increase anymore. And that's more or less what is written here. So you start with L equals to your observable set. And then for each of these matrices that appears in the decomposition of the Jacobian, you just multiply L times this, and for each row you check, is this row in the span of the rows of my lumping? Yes or no? If no, then I add this new row to the lumping and continue. If after one go you have added a row, then you repeat just in case, just to make sure you don't need to add anything else. And if you do one go on all of these and you don't add any row, then by definition, you are invariant under these matrices, and that's precisely the definition of a lumping. So you have reached a lumping that contains, by construction, your observable set. So this is the previous work on constraint lumping, and this is CLUE. This is the main algorithm that has these nice properties. So the check, this check over here, that is kind of a very interesting part of a vector being in a subspace is done using Gaussian elimination. So you basically keep L in a row echelon form, and whenever you want to check if a vector is in there, you perform the elimination. If it's all zeros, it's in the space. If it's not zero, then you already can add this new representation into the matrix. You compute the corresponding steps of the row echelon form, and you can proceed forward. And then you keep it in a nice way. It's quite efficient to compute, and it's quite simple to implement in that regard. This algorithm was also extended for rational functions. So far, this criteria of decomposing the Jacobian was stated in the talk for polynomials. And in a recent work, we extended it to rational functions. So now you have a different type of decomposition, but it also works, no problem. And everything was implemented in Python and SymPy, and is available freely. So when whoever wants to use Clue, it's more than welcome to use it. And then, of course, it's okay, we have Clue, perfect tool. It computes exact constraint lumping. So why do we want to have a numerical clue? Well, in practice, whenever you use these techniques in biology or wherever, usually the coefficients are not exact numbers. They are usually approximate values that they compute by experimentation. Sometimes they are integers numbers and they love it, but sometimes it's just a set of numbers that you can represent as rational, but usually they contain some error or noise in the number. And exact lumping is very sensitive of this. So if you have, for example, this system over here, that it was from the previous example, it has and you apply Clue to this observable matrix, which is basically observing X1, we got a lumping, perfect. But now if we just slightly change one of the coefficients, in fact, you can put not only 4.05, but any epsilon, I think, almost, you will find that there is no lumping anymore. And then it's like, yeah, but maybe this small difference between the exact value and the value that I know is not very, it's just noise from the data. So can we use a different technique that will allow us to do the same lumping technique? So we will reduce the model and, okay, we are not sure if this is the exact data, so we may have some errors at the end of the day, but can we do this reduction and keep control the errors at the end of the day, so we can do simulations and extract information from the model, right? Even though the numbers are not exact. So with all of that, let me start with numerical clue. The idea, and the main idea, and it's in that regard is nothing fancy, it's just, okay, can we, as usually whenever you have something numerical, can we just allow a small error, a small epsilon error when we add new rows to the lumping? In that way, if you will look to the algorithm of Clue over here, the part that this is done when you add a row into L is just when the row was not spanned by the row space of L, right? So you can change this just to allow this small error. So you add an epsilon, that is the maximal distance you will allow to your vector to differ from the subspace, and then the whole algorithm will still works, no problem. And and this will include in particular exact Clue, in the sense that if you put epsilon equal to 0, then this is exactly Clue. Yes. Now the question is, before the membership, this membership checking was done using Gaussian elimination. And now we have this distance checking. Is it worth it to keep the Gaussian elimination? I mean, it has many advantages, as I have already said. It's simple to implement, it's very understandable. It keeps the basis of your subspace L kind of in a row echelon form. It's very good for exact data. However, there is one inherent problem with numerical algorithms and the Gaussian elimination algorithm, that at some point when you have a new vector, you have to pick a pivot, and that has to be not 0. So if something is very close to 0, then you may have some issues dividing by that because it will make things too big, or maybe it was 0, so you need to add some tolerance there. It can be solved. This problem can be solved. Yes, I agree. The thing is, once you have this, you have your new vector, you you perform the Gaussian elimination to see if it's in the subspace. And now you have to see, okay, I have a vector and I have to measure the distance from this vector to my subspace. This is additional operations that can be done. Yes, again, can be done, no problem, but it's spending more time in this step that we would like to. And all these numerical problems kind of are a bit annoying to the implementation. So it seems that this Gaussian elimination is not that appealing, at least on the first glance, for numerical data. So we essentially propose a new approach for checking this membership or checking this distance, which is essentially computing the orthogonal projection of the vector onto the space L, generated by L. And in that sense, it's quite easy to see that if you have L that generates as a vector space, and you have a vector in the ambient space, if you project this vector and it remains the same, fixed, then the vector was already in the space. Otherwise, it's not. And this can be expressed in this formula over here. So the vector is in the space if and only if the difference between the vector and its projection over L has norm zero, essentially is the zero vector. And why this is interesting? Because this projection can be computed quite easily by this L bar L, where this L bar is the Moore-Penrose pseudo inverse of L, essentially having this nice property. And more importantly, and this is kind of the nice part where everything helps, is if L is orthonormal, so all vectors are orthogonal among each other and they have norm 1, then this L bar is just a transpose. So it's quite easy to compute, and you can compute the PL on the fly quite nicely. Yes, so in the and this is kind of goes in a similar way as in the exact case, where whenever you have you perform this Gaussian elimination, the result of performing this Gaussian elimination tells you if it's in or not, and then you can reuse the same result to add the new vector, right? And here it's kind of similar. Now you project orthogonally, you check the difference, and if it's in this, and you can check the distance now very easy. It's just the norm of this vector, as you can see in this picture. So you have a vector, you just project it, and then you check the difference in the green line. And this vector that you get already tells you the distance. You don't, in the Gaussian, if you do Gaussian elimination, this was not as straightforward. You need to do more operations, which essentially is doing this orthogonal projection. And then, yeah, all these operations kind of change very nicely one with the next one. So we essentially design a new algorithm saying changing this membership from the Gaussian elimination to the orthogonal projection. And the whole algorithm will kind of look like this, where it's the same algorithm as before, but now we just expand this membership part in the middle, where now, as usual, for each row that we are going to check, we just compute the projection, we just check the difference, and this is just the remaining part, and then we check the size. If the size is big, then we need to add it. So we just normalize it to keep an orthonormal basis. And then we add now this new vector to the matrix. As a consequence of all the operations we've been doing, this is already an orthonormal basis. We don't need to do anything else. And then updating this PL is quite straightforward. It's just computing the scalar product of this new vector with the other vectors and putting in appropriate positions in a bigger matrix. So all of this is quite easy to perform. And then you just do as we said. You just repeat this, you check if the vector is big, you add it. If the vector is small, you don't add it and keep moving. What this will lead to is sometimes in the exact clue, you add vectors because they are non-zero, but they are very small. And in this case, we skip those. So we always get something smaller. So always get the same or smaller versions of our model. Of course, if we don't add a vector that was not zero because it was short, then we will have probably an error in the final simulation at the end of the day, but we will dive into that a bit later. So let me come back to the example that we had before. We had this error in one of the coefficients, is 4.05. And with exact clue, we have no reduction. But now let's just run this numerical clue with epsilon equals 0.1. And let me just go through all of it a bit, step by step. This is the Jacobian of that function. So you can see that the derivative of x1 prime with respect to x1 is 0, and so on. You just compute all these partial derivatives and you get this matrix over here. And now we do this decomposition that was inspired by clue. And we get that this Jacobian matrix can be expressed as a sum of 3 matrices where J1 is multiplied by the constant monomial. The J2 is multiplied by x2 and the J3 is multiplied by x3. And these are J1, J2, and J3. It's true that sometimes these matrices are a bit boring or too sparse. They may have rows full of 0, but that's not a problem for us. We just do the operations and check what happens. So we start. The observable was the 1, 0, 0 because we wanted to observe x1. So now we start with this row. We multiply this row by all J1, J2, and J3, and we obtain these 3. So let's start analyzing the first 0, 0, 0. Well, this is easy because no matter what we have, the projection is 0 vector, and the norm of the 0 vector is 0, which is smaller than 0.1. So we forget about this vector. Now, the second vector, more interesting. Now we do the projection, and in this case, this vector and the vector that we have is orthogonal. So when we do the projection, we get 0 because there is nothing there. And then we get that this difference is just the whole vector by itself. Now we check the norm of this vector and we see that is bigger than 0.1. In fact, it's bigger than 1 because we have a 2 and a 4.05. So we normalize and we add this normalized row to the matrix L. And I just show you here, this is the normalized row, and then you just add it. Now we have bigger L, and now we check the last one, the last vector that we were checking. In this case, now we project with this new L, and in this case, the difference between this vector and its projection is this vector, which we have 0, 0.076, and minus 0.046. In this case, we compute the norm of the vector. It turns out to be 0.089, which is smaller than 0.1, so we forget about this vector. And in fact, this is where the main difference between this and exact clue will appear. Here we have something that is not 0. So in exact clue, we will add it to the reduction, getting a 3 times 3 matrix and then having no reduction. But here, since it's close enough, we don't add it and keep going. So now we take the second row and we do the same. We multiply by J1, J2, and J3. And in this case, the first vector is non-zero. It's minus 0.011, minus 0.897, and so on. And if we check it out, we project into L, we check the difference between this vector and its projection, and we get a nice vector that has norm 0.02, which is again smaller, once again, smaller than 0.1. So we forget about it, we don't add it to the matrix. And the last two is just 0, 0 again, nothing to do here. So since we have no more rows to analyze in L, we finish. And this is the approximate lumping that we get using epsilon 0.1 for that changed system that we have from the beginning, right? And in fact, it's very interesting to see here that this lumping that we got is exactly the exact lumping of the original system using exact clue, right? So essentially, you made a mistake in the system, and allowing a small error in your lumping technique, you are able to recover something that was true before. That's more or less one of the ideas behind numerical lumping. So, as I was saying before, with numerical lumping, we can compute exact lumping. You just fix epsilon to 0, and then you have a an exact lamping algorithm that is essentially changing how you check membership by changing Gaussian elimination with orthogonal projections. Theoretically, there is no, there is no big difference. There is just more about the implementation. Then if, as we have just seen in this example, if the system has a small numerical error in some coefficients here and there, we can recover the original lamping, having the true coefficients here and there that we don't know. Although there is no actual tool to check that out right away, but this is something that to keep in mind. And another idea that is behind numerical lamping is, okay, with exact lamping, you reduce the model up to here. Maybe if I allow some error in my simulation later, I can reduce it even more. So I speed up my simulation even more, although I will commit some errors. Okay. So, and in that regard, right, talking about the error, we can have a bound on this error, having some conditions here and there, right? So one of the results is bounding this error. And for that, let me just define what the error is precisely. So let's take x of t a solution of the system, the true solution, essentially. And let's consider L an orthonormal matrix, which kind of be the output of our algorithm. Now, let us consider y of t the solution of this system, which is exactly the reduced system we had when L is a lamping. If it's not a lamping, then this is not exactly a reduction, but it's very related. This is the system you will get out of the algorithm, and you fix the original the original condition of y to be just the lamp version of the initial condition of x. So essentially, it's like if everything would be a lamping, the error will be 0. But in this case, now you have that. You take the solution, you just lamp it with L, and you check the difference for what would you have gotten by simulating the reduced system at the same time. And the difference is the error that we're looking at. As I said, if L is a lamping, then you can prove very easily that this y is exactly this L of x, which is the expected thing. But here, since we don't have an exact lamping anymore, then usually this function E will be non-zero. So now, with this definition in mind of the error, we can have this nice and short theorem around that basically says if you start in a bounded set of initial conditions, so you don't exactly where, but your initial condition for x is in a bounded set, then you fix a time horizon capital T, and the system, the original system, is well behaved. Essentially, it does not explode in that time period for all the initial conditions in your set S. Then you can bound the error for an L. So if L, which is an orthonormal matrix, was computed using epsilon as a tolerance during the numerical clue, then there exists a constant that depends on the function, the initial set, the matrix, and the time, such that the error is just linear on epsilon times this constant for all the time values. In practice, this constant is a bit big. Well, in practice, not. In theory, the constant is quite big. If you want to check all possible cases, then this constant that goes through with epsilon is quite big. But once you have this constant that does not depend on epsilon itself, you can just keep reducing epsilon more and more until you get an error bound that you're happy with. No problem. Although at some point, if you reduce it too much, you will get just the exact reduction, which then will go against your original intention. But that's a different story. So this is this is numerical clue. This is how it works. This is how the error just goes here and there. And I was saying this bound in practice is in theory is big, but in practice, the error that you commit is not as big sometimes. When you have small epsilons, you get more reductions than error you make. So let me show you some experimental results out of it. And for that, we took 3 models from biology, very common in these benchmarks for clue and other model reduction techniques. I won't even dive on what these models means. The thing is, usually they have a set of differential equations, and they usually like to observe one of the variables that is somehow information they would like to get out of the system. So for that, just let's jump into the nice old table. So let us focus on the first experiment, this BioNet Gen. It started with 87 variables, and after performing clue, just exact clue, it gets reduced to 30. It's a nice reduction, I have to agree. But now if you start adding a bigger epsilon, so this column is the epsilon we allow, and then we run numerical clue with this epsilon, it turns out that the size of the system can be reduced even further from 30 to 23, 9, 5, 4, and you can even just collapse it into 1 if you keep increasing epsilon. And in the right-hand side, you can see the time. The time is not, I mean, it's not, the more you increase epsilon, the fewer time you have, because then you have fewer steps at some point. And then maybe the most interesting column is the error. The error, when you get the exact lamping, it's very small, as expected. And then when you start increasing the epsilon, so reducing the system, the error just grows until just no information is preserved. So this is not a good epsilon to be used for this case, right? So now let's go to the second experiment, these NIMS and many numbers. It started with size 24, and the exact lamping was 19, size 19. And in this case, is one of those cases where this exact numerical clue, sorry, is not so nice to apply it, in the sense that it does not provide much more. Here we have that for small epsilons, we get the exact lamping. This is the first row. If we increase it a bit, we get 1 fewer variable without committing a big error. That's true. So this could be used. And then the next step, so the next reduction that we get jumps directly from 18 to 8. And then the error is stupidly high. So we just collapse all the dynamics essentially from here and lose all the information in this reduction. So this is not as good. And finally, this is then the other type of application of this numerical clue is the last example, because this is very interesting. In this case, we started with 62 variables, and the exact lamping, as shown here, provides no reduction. You have the whole system, there was nothing to reduce. Okay, but then if you just provide a very small epsilon, 0.00079, and you run numerical clue, you get a system of 28 variables, which is less than half. And in this case, the error that you commit is very, very small, and it's insignificant, essentially. It looks like an exact reduction somehow. And this is kind of inspiring a bit. This the system had maybe some small mistake or some numerical error here and there that you missed while building the system. And now with numerical clue, you can recover right away. So maybe analyzing this reduction is even more insightful than leaving by itself. So as we can see in this table, depending on how we pick epsilon, we get a nice result, we get a trashy result because it gives no information. So how can we pick an appropriate epsilon? This is maybe one of the most complicated tasks, because either you run things many times and compare, and then you are losing the idea behind of being fast, or you just guess a value with some heuristic and then hope for the best. In those lines, let me just remark, there is one maximal epsilon that you can choose from, in the sense that if you pick something bigger, you will not do anything. You will keep your observable matrix by itself, and all the checks you do while the algorithm will say, do nothing, do nothing, do nothing. You don't add anything, and then this is it. And this is something fixed. You can compute it, right? And then another thing that is kind of clear is, as long as you increase epsilon, the reduction of the reduced system can only decrease more and more until you just collapse everything. And this is kind of shown in this picture. This is from the Bionet gem because it has so many steps. And here on the left, we see when we increase epsilon until its maximum, the size of the reduced model just jump down and down in small or bigger steps from time to time. And all models have this type of stair graph here and there. And then on the right-hand side, we have plotted the simulation of the observable that we were interested in from the beginning. The blue line, which is hidden here behind, is the true value. And then we have depicted the values after performing clue with the orange, green, red, purple, and brown. And we can see it's essentially what the table was saying. When the epsilon was small enough, so when you were here, you have no extra reduction with numerical clue, you are perfect, you are in the exact case. If you go a bit below and you reduce something more, you create some error, but somehow similar behavior, and in some cases even meaningful because they're interested in some steady cases and how much time it takes. And in that case, it's quite similar. And the more you increase epsilon to the maximum possible, the bigger the error becomes until nothing happens to the variable because you just do nothing. And this is kind of the collapse of the whole system. So picking an appropriate epsilon is difficult and it's not trivial to do. We provided some heuristics, most on the lines of forcing a minimal reduction. So you give, because all these heuristics have to work without performing clue in a first run. So you give me the model and I will find an epsilon such that you will reduce the model to 80%, kind of. And then if it's something bigger, you can get something better, you do it. But if not, you force it to go to this stair until you reach an 80% size, and then you stay there. And then you hope you don't get a big error out of there. But this heuristic has to be improved. In fact, we are thinking on others, but none of them has worked very nicely so far. And yeah, and I think with that, I can start my conclusions. Yeah. So in this work, we basically have extended exact constraint lamping to approximate constraint lamping with all the usual trade-offs from exact to numerical algorithms. And one important thing is that this new approach is a direct extension of the exact case. So in fact, you can recover exact lampings with this, and it's still working in polynomial time, as Clue was doing. And we have successfully tested out and find extra meaningful reductions in some models in real cases. As a future work, first, let me remark that in the same way that Clue was working with polynomials and rational functions, this approximate Clue will work also for those cases, but we still would like to extend it to other vector fields. One of the key points of extending for rationals or any other thing is you don't need to split into monomials. Maybe you can just evaluate the Jacobian in many points and then hope for, and then you stop at some point because you fill a vector space. This maybe can be done using numerical evaluation, but there are many problems there. You need kind of exact evaluations of your Jacobian, and that leads to problems. So we are working on that a bit, and maybe if we manage to accomplish or go above all these problems, then we may allow different type of vector fields in the systems. As I was saying, we will also explore more heuristics, trying to see how they influence the error that we get and so on, and how often they work. And finally, the part of the theory that we did not cover so far was how confident are we that we can recover the true reduction from a perturbed system. So if you have some error in your system, it seems you can recover the true lamping, right, out of the numerical clue with some epsilon, but we will need to work out how much how big the epsilon can be in compare with how much error you make in the system and so on. So there is many things to think about it. and it's part of the future work. So I think, yes, that would be it for me today. Thank you very much for listening, and I'm open for any question.
Okay, yeah, thanks, Antonio, for this really nice talk. Do we have any questions or comments? Just unmute yourself and ask, or if you prefer, you can also type in the chat.
I have some questions.
Mm-hmm.
Thank you, Antonio. This epsilon, how does it fit into the problem statement? Can you make a problem statement that includes the epsilon?
In the sense that, in what sense exactly?
Oh, I need to mute. Yeah, we have in the room. We have this echo. Just sorry.
Yeah. So the question, I don't really follow the question in what way. So you mean that how can I include epsilon to reflect the final error I will make, or what sense?
Let me put the headphones on. Maybe yeah, it'll be easier.
One second.
Okay, you muted. Okay, good. Can you hear me now?
Yes.
Okay, good. Yeah, sorry about that. So you put you add the epsilon to the algorithm, right?
Yeah.
So what is the problem that the algorithm is solving?
So it computes the minimal. Yeah, let's go here. Yes. So it's the minimal lamping. I don't want to say lamping. It computes the minimal space L such that for all the rows, so all the rows on L times JT, the norm is smaller than epsilon. So the input, the problem has two inputs, is the system itself, and well, it has three inputs: the system, the observables, which was the inputs of clue, and then you have also epsilon, that is a free thing in your algorithm.
Right, but so far it looks like this epsilon, So you're given your system, and you suppose you're given epsilon.
Yeah.
Just once again, could you say it again? How exactly is epsilon factored into the output of the algorithm? So you showed the code, but can we go back to the problem statement and try to put epsilon there into the problem statement?
But where exactly? I think I didn't even put the problem statement by itself, right? So
I missed the first like 5 minutes, so I wasn't sure.
So in the talk, I just basically said what a lamping was, right? And then you compute the minimal lamping such that the observables are in there, right? That's clue. So the numerical clue will be the minimum, the minimal space generated by L, such that for all the yes. So in all this decomposition, these rows have. In the original clue was these rows are in the space. Now is these rows have a smaller size than epsilon.
Okay, so this is so far epsilon is sort of indirectly, internally accounted for.
Yeah,
that doesn't really appear as a external for the problem statement.
And in part, choosing this epsilon in order to make things meaningful is tricky because of the at the end of the day, you want to make the error small, and the bound of the error depends on the F and the L. So all of these things get involved at the end of the day, right? You would like to have something like, let me, where is it? Here, right? Here you're saying that for all x's, this is exact lamping. For all x's, these rows that are generated here are included in L. And now you would like to have something like all my rows will be, so all these values will be small, essentially, will be close to my space. but that's a bit overkill. And in fact, you can show that at the end of the day, but the bound that you put there, it's different from the epsilon. So there is a hidden relation there that I did not show here because it was a bit too convoluted, but yeah.
Thank you. And in your table with errors, with your examples, right, so this E of t, could you just show the definition again?
Yeah,
This was
so
the difference between...
It's the difference between the, so X will be the solution, the true solution, then you apply L to compress it. And then
yes,
Y is the solution of the reduced model with the appropriate initial value.
Yes, and how do you choose the big T?
The big T was chosen using the, I forgot to say that indeed. In these papers that they describe, they analyze up to some point, to some time. So we use that time, and because it was a meaningful time. So it's something that to analyze the error at the end of the day, you need to fix. And it's also part of the input if you would like to see it that way. So the user would say, I would like to analyze until 10 seconds. Then that's your big T. Going further than that, it's not that necessary anymore.
And how do you find the Y of t?
In these cases, we compute the lamping itself, right? So we compute the numerical lamping, and then we just do both simulations, the true simulation and the reduced simulation, and compare the values essentially.
And
so this, yeah.
Sorry.
No, so this table involves more work than you usually do. You don't usually do that. You don't usually compute the whole error because you will not know it, because you will not simulate the true value. You will reduce it and hope it's good. And for that is why the heuristics are important, because if you can have some guarantee or some hint that this epsilon will work nicely, then you kind of check, or you can check a posteriori that things are going good for the reduced model, right?
And yeah, and when you do simulation, is it what is it, numerical solving, or what is it?
Yes, we use a numerical solver there, which is what these people tend to use at the end of the day to study these systems.
So it does not give you a guaranteed answer, right? So you can't really rely on numerical solver, right?
Yeah.
But still it's some good, hopefully good way to but then so in this table you use a numerical simulation for the original, right? The original system, which is supposed to be hard to solve, right?
Yes. So that's why our experiments are of small dimension, essentially, right? We don't get bigger than 100.
Yeah, and this is probably suggesting that you wouldn't have access to such a table for real systems you want to deal with, right? So you don't know the error.
Yes, and that's one of the main drawbacks of this approach. You have you don't have a big guarantee a priori that things will work. I mean, you have the bound, but the bound is not small in practice to have it. Usually things will get close. It's the usual hope with numerical things, but in theory, the bound that the result is giving, this bound over here, it's not pretty.
Well, like, what kind of numbers are there? Like, is it...
I mean, it's just big, right? It's just a big number because it's an exponential that depends on the size of the initial conditions, the size of how much it will grow, and also, and for that you use, in the case of F being analytical enough in your solution, right? So if it has a singularity, then this won't work. But if you have a region that things will work nicely for the solution, right? It does not explode, then for these analytical functions, if it's Lipschitz, then you have this Lipschitz constant that allows you to build this bound at the end of the day, and it will be an exponential of those constants over there. And in practice, it makes things like, yeah, your error will be smaller than 2 million. Yeah, but we are working with numbers of 2. Yeah, but it's more than 2 million. Okay. So yeah, that's the main problem of this approach.
Thank you. I have a few more questions, but maybe somebody else wants to ask. Okay, let me ask if you don't mind. So you showed so in your performance table, you also showed the time used to compute.
Yes.
How does this compare with the exact timing?
It's usually faster than the exact timing. In fact, you can see here the exact timing is usually the first row because it's the exact reduction, and the steps are kind of the same. It's usually faster, but it's difficult to compare because the tool behind is slightly different. For some cases, I found that this one tends to work faster because you have these numerical values more easily, and in the other case, the numbers just grow because they are just exact somehow. But at the end of the day, they're very much comparable, and the gain you get from lumping with this numerical error is not worth it, a remark in these cases, usually. Also depends a lot on the matrices that appear. If they are if they are sparse, things usually get sparse at the same time, and it depends a lot of the optimization you do behind. I remember of working with Clue, the actual implementation, and there are so many tweaks to make things more sparse to work better with Gaussian elimination that things get faster in some cases, slower in other cases. So it's very difficult to compare the both approaches, but one baseline would be to check just the first row. And essentially the number of operations you do is smaller, right? Big operations, not multiplications and such. I don't know if that answered your question.
Thank you.
Okay.
And have you thought about generally other kinds of dynamical models like discrete time models and maybe delay models? And have you thought about nonlinear reductions?
Yes, I have think about it, and I don't have a precise answer for any of those. I'm afraid for discrete times, I have used these techniques and they just work, right? So you can just compute the same type of lampings in a discrete time system where instead of having derivative equal function is the next value is function of the previous function of the previous value. So these dynamical discrete time dynamical systems. And for when they are polynomial, they're rational, the whole algorithm works exactly the same. The meaning at the end of the day changes slightly, but it works. And then you can have this numerical lumping once again, somehow. And okay, the meaning of that, it will change because now you don't have a differential equation. So the error meaning is lost, right? You don't have a continuous time. So maybe that's a bit tricky. But what I can tell you is there are some models that, so one of the applications of this is, and in fact is one of the problems unsolved, is when your model is slightly wrong, can you recover the true thing without, right? When you have a small error in your model, can you recover the true reduction? And in fact, that's something that we've explored in some discrete time dynamics, where this input is given by floating point numbers and they are quite messy and the system do stuff to them. And then we recover actual reductions that then afterwards we can check and prove that they were true reductions in theory, exact reduction. So, but that's a different point of view. And that's for discrete. You mentioned then also the nonlinear reduction. For that, I would love to work more on that, but I didn't have time to really dive into it. It could be very interesting to see how it works and if any of these bounds or results can be extended into that. I mean, at the end of the day, you can just run the algorithm. The only thing is you need to be more precise in what are you checking, right? Here we are checking that you are in a subspace, but then you will need to check a different story, right? Because the reduction is nonlinear. So first, I will need to see how the nonlinear reduction will work in general and then jump into the approximate one for sure.
Yeah, thank you.
Welcome.
Okay, so if there's no more questions or comments, let's thank Antonio again.
Thank you.
And so, yeah, so we there's not going to be a talk next week because it's a holiday, but there's going to be a talk in 2 weeks, and it's going to be again at the usual time for everyone.